Hello, and welcome to another gentle journey on Sleepy Professor Stories. Tonight, we are not chasing explosions or standing at the edge of drama. Instead, you are invited to see volcanoes as something slower, something quieter, as steady breathing places of the earth. Beneath every mountain shaped by fire, there is warmth rising patiently through stone, not in a rush, but in rhythms that stretch across thousands and millions of years. Volcanoes are not sudden interruptions in the landscape. They are part of the landscape's long conversation with heat. Deep below your feet, far beyond soil and bedrock, the planet holds layers that remain warm from its earliest formation. That warmth does not disappear. It moves slowly upward, carried by subtle currents within the mantle. Rock at those depths is not quite liquid and not quite solid. It behaves like thick wax, softening under pressure, shifting almost imperceptibly. Over vast spans of time, pockets of molten rock gather there. This molten rock, which scientists call magma, forms when pressure decreases or temperatures rise enough to allow stone to melt. It waits in chambers hidden from sight, held beneath the crust like a quiet thought waiting to surface. You can imagine the Earth as a living sphere that releases heat in measured breaths. Volcanoes are one of the ways it exhales. When magma finds a pathway upward through cracks or weakened crust, it rises because it is lighter than the surrounding solid rock. Sometimes it pauses, cooling slightly, crystallizing minerals within it. Sometimes it continues, reaching the surface as lava. The journey is rarely hurried. Most magma never erupts at all. It cools underground, becoming granite or other igneous rock, strengthening the crust from within. Across the planet, volcanoes appear where tectonic plates move. These plates are enormous slabs of lithosphere that drift slowly over the softer mantle below. Where they pull apart, magma can rise gently into the gap, creating new crust beneath oceans. Where one plate slides beneath another, water carried down into the mantle lowers the melting temperature of rock, encouraging magma to form. And in a few places, far from plate boundaries, steady plumes of heat rise from deep within the mantle, building islands in the open sea. All of this unfolds in silence. The dramatic images you may have seen are only brief moments in a far longer story. Most volcanoes spend the majority of their existence resting. Snow gathers on their peaks. Forests grow along their slopes. Animals nest in craters long cooled. The mountains stand still, but deep below, warmth circulates patiently, like a slow heartbeat. As you listen, there is nothing you need to solve or memorize. These details can drift past you like warm air rising through stone. If a fact settles gently in your mind, let it rest there. If it floats away, that is perfectly fine. The Earth will continue its steady processes, whether or not we hold every detail. Volcanoes have shaped continents over immense stretches of time. The crust beneath your feet was built, in part, by ancient eruptions that spread lava across vast regions. As lava cools, it forms basalt or andesite, depending on its chemistry. These rocks become the foundation for future landscapes. Rain falls upon them. Wind softens them. Rivers carve through them. What begins as molten brightness eventually becomes quiet terrain beneath grass and trees. Even the gases released by volcanoes have played a role in shaping the atmosphere. In Earth's distant past, volcanic outgassing contributed water vapor, carbon dioxide, and other compounds that helped form oceans and influenced climate. The air you breathe tonight carries traces of cycles that began long ago in volcanic chambers. It is a gentle reminder that the planet's inner warmth has always been connected to life at the surface, and life often returns to volcanic land with surprising calm. Fresh lava appears dark and barren, yet over time it weathers. Tiny cracks form, moisture gathers. Lichens and mosses begin the slow work of turning rock into soil. In this way, destruction is rarely the final word. Renewal follows heat, though it may take years or centuries. If you find yourself imagining distant islands rising from the sea or snow resting on a silent crater, allow that image to remain soft. There is no need to sharpen it. Your breathing can slow now, matching the slow pulse of the planet itself. Shoulders soften, jaw unclenches. The story we are entering stretches across oceans, forests, ancient villages, and even distant worlds. Each place is touched in some quiet way by the steady movement of heat beneath stone. If these gentle explorations bring you comfort, you may choose to subscribe or leave a small comment sharing where you are listening from. But there is no urgency in that. The mountains are not in a hurry, and neither are you. For now, simply notice the idea that beneath every landscape lies motion. Slow, patient, almost invisible. Volcanoes are not merely events. They are part of Earth's long rhythm, its way of releasing energy and reshaping itself over time. In the chapters ahead, we will move closer to these mountains, tracing how molten rock gathers, how pressure builds, and how landscapes slowly rise from repeated flows. But for this moment, you are resting at the threshold, aware of warmth beneath stone and time unfolding gently in every direction. Let's begin. Beneath your feet, far below the quiet floor of your room, the earth is warm. Not warm in a flickering, restless way, but in a deep and steady way, like embers that have glowed for billions of years without going out. You do not feel this warmth directly. Layers of soil, rock, and crust cradle you safely above it. Yet the planet beneath you is never completely still. It holds heat from its formation and from the slow decay of natural radioactive elements within its interior. This heat does not rush. It lingers, circulates, and patiently rises. As you imagine descending through the crust, you pass solid rock that seems unmoving. But over immense spans of time, even solid rock can bend and flow. The mantle beneath the crust behaves not like brittle stone, but like something softer when given enough pressure and time. It moves in slow convection currents as warmer material rises and cooler material sinks. These currents are gentle on the scale of a human life, yet powerful enough to shape continents. Pressure increases as you move deeper. Temperature increases as well. In certain regions, these conditions allow rock to melt. The melting does not happen all at once. It begins in small pockets, where minerals with lower melting points soften first. The result is magma, a mixture of molten rock, crystals, and dissolved gases. Magma forms quietly, without spectacle, in chambers hidden many kilometers below the surface. This molten material is less dense than the solid rock around it. Because of this, it feels a subtle upward pull. It does not leap toward the surface. It seeps, searching for weaknesses, following cracks, widening them slowly. Sometimes it pauses in reservoirs within the crust, cooling slightly, allowing crystals to grow inside it. Quartz, feldspar, and other minerals begin to take shape as the magma lingers. You might picture these chambers as vast glowing lakes, but in truth, they are often complex networks of interconnected pockets and veins. Some remain molten for thousands of years. Others cool and solidify without ever reaching open air. When magma cools beneath the surface, it becomes intrusive igneous rock, strengthening the crust from within. Granite mountains you see today were once molten bodies resting deep underground. The movement that allows magma to form is tied to tectonic plates, those enormous fragments of lithosphere that drift slowly across the mantle. Where plates pull apart, the pressure on the mantle decreases. This drop in pressure allows rock to melt even if temperature remains the same. It is a gentle release, like loosening your grip on something warm. Along mid-ocean ridges, this process continuously creates new oceanic crust. Where plates converge, another quiet transformation unfolds. One plate may slide beneath another, descending into the mantle. As it sinks, it carries water trapped within minerals. That water lowers the melting point of the surrounding rock, encouraging magma to form. In this way, water deep within Earth plays a subtle role in shaping fiery mountains. In other regions, far from plate boundaries, plumes of unusually warm mantle rise from deep within the planet. These mantle plumes remain relatively fixed while plates drift above them. Over time, they create chains of volcanoes across oceans. The islands appear one after another as the plate moves, each one marking a place where heat once reached upward. The gases dissolved within magma are important as well. Water vapor, carbon dioxide, and sulfur compounds remain trapped under immense pressure underground. As magma rises and pressure decreases, these gases expand. Their expansion can drive eruptions, but long before that moment, they influence how magma moves and evolves. Gas content affects viscosity, determining whether magma flows easily or resists movement. Viscosity itself depends largely on silica content. Magma rich in silica tends to be thicker, more resistant to flow. Magma lower in silica flows more readily, spreading across landscapes in smoother sheets when it emerges. These differences begin deep underground, long before lava ever touches the sky. Temperature also shapes magma's behavior. Hotter magma tends to be less viscous, allowing gases to escape more easily. Cooler magma becomes stickier, trapping gases within it. These characteristics develop gradually as magma rises or stalls, cooling in stages. You may notice how none of this is hurried. The Earth does not force its heat upward in a single burst. It circulates warmth through layers, guided by physics that remain steady and patient. Convection currents continue whether anyone observes them or not. Plates drift at rates similar to the growth of your fingernails. Magma chambers fill and empty over centuries. Sleep reminder here. Let your breathing slow to match this steady planetary rhythm. There is nothing you need to do with this information. You are simply listening to the quiet mechanics of a living world. Even earthquakes, often associated with tectonic movement, reflect the gradual accumulation of stress along plate boundaries. Stress builds slowly as plates press, pull, or slide past one another. When it releases, the motion may feel sudden at the surface, but the build-up took years, sometimes centuries. Within magma chambers, crystals continue forming as temperature shifts. Some sink, some remain suspended. This internal evolution changes the chemistry of the remaining melt. Magma is rarely uniform. It is dynamic, responding to subtle variations in pressure and temperature. Over time, pathways open. Fractures extend upward through brittle crust. Magma exploits these weaknesses, rising in dikes and sills, intruding into surrounding rock. Some intrusions remain frozen in place, creating vertical walls of hardened basalt or horizontal sheets of dark stone. The boundary between solid and molten is not sharp. It is gradual. Rocks soften before they melt completely. Crystals begin forming before magma cools entirely. Everything transitions gently from one state to another. As you rest here, imagining these processes far below, you might sense the Earth as a vast circulatory system of heat. Energy moves from deep interior towards surface, then radiates into space. Volcanoes are only one expression of that transfer. They are places where internal warmth meets the open air. But before any mountain rises or lava flows, the story begins in these hidden chambers, in pressure changes and mineral shifts, in convection currents turning endlessly beneath continents and oceans. In the next chapter, we will rise slowly toward the surface and explore how repeated flows of lava build mountains layer by layer, shaping the quiet architecture of volcanoes over time. When you look at a volcanic mountain rising against the sky, it may seem solid and permanent, as if it has always been there. Yet every volcanic peak is the result of countless quiet events layered gently over time. No volcano appears fully formed. Each one grows through repetition, through steady additions of lava, ash, and stone. It is less like a sudden tower and more like a patient sculpture shaped by many breaths. Imagine the first flow of lava spreading across bare ground. It moves outward, cooling as it meets air or water. The outer surface hardens first, forming a dark crust, while molten rock continues to glide beneath. Eventually, it slows, thickens, and becomes still. That cooled surface becomes the foundation for the next flow. Over time, layers accumulate, one resting upon another, building height so gradually that no single generation could witness the entire process. Some volcanoes spread wide rather than tall. These are often formed by lava that flows easily, low in silica and high in temperature. Because the lava is fluid, it travels far before solidifying. Each eruption adds a thin sheet, expanding the base outward. Over many eruptions, the mountain grows broad and gently sloped, like a shield laid upon the land. You can picture its sides rising slowly from the earth, smooth and expansive. Other volcanoes rise more steeply. When magma contains more silica, it becomes thicker, resisting flow. Lava emerging from such magma does not travel far. It piles up near the vent, creating steeper sides. In addition to lava, these volcanoes often release ash and fragmented rock, which settle around the summit. With time, alternating layers of lava and ash build a tall, symmetrical cone. Each layer records a past eruption, preserved like pages in a geological diary. There are also smaller volcanic forms, shaped primarily by loose fragments. When gas-rich magma erupts and breaks apart in the air, pieces of lava cool as they fall back to the ground. These fragments gather around the vent, forming a cone of cinders. The slopes of such cones are often steep, but relatively simple in structure, built mainly from accumulated pieces rather than extensive lava flows. Even these modest formations speak of repeated activity, of material rising and settling again. No matter the type, the construction is always gradual. Eruptions may seem dramatic in brief moments, but between them lie long intervals of quiet. Rain falls on cooling rock, wind carries fine ash away, plants begin to anchor in cracks, the mountain rests, and then, perhaps decades or centuries later, Another eruption adds a new layer. You might imagine standing at the base of one of these mountains, be aware that beneath your feet lie hundreds of individual flows stacked upon one another. Each flow once glowed with heat, each cooled into stone. The mountain is not a single event, but a history of many gentle additions. Gravity shapes these structures as well. As lava accumulates, its weight presses downward, compacting older layers. Ash layers settle and compress, gradually hardening into tuff. Over time, erosion begins its patient work. Streams carve channels into slopes. Frost wedges open small cracks. The mountain is always being built and reshaped at once. The central vent of a volcano serves as a pathway connecting deep magma chambers to the surface. Around this conduit, rock may fracture repeatedly. New vents can open along the flanks, allowing lava to emerge from different points. This spreading of activity further enlarges the mountain's footprint. What begins as a single opening may become a network of fissures. In broad shield volcanoes, successive flows can create overlapping lobes, each slightly different in direction. The landscape becomes a mosaic of hardened waves. In stratovolcanoes, the interplay between viscous lava and explosive eruptions creates alternating textures. Some layers are dense and solid, others porous and crumbly. Together, they form a complex structure capable of standing tall for thousands of years. Sleep reminder here. Let your body soften as you picture these layers stacking slowly, one upon another. There is nothing you need to measure or remember. The mountain grows at its own pace, and so can your thoughts drift gently now. Temperature influences the shape as well. Hotter, more fluid lava forms thinner layers. Cooler, thicker lava builds steeper profiles. Even small variations in chemistry lead to noticeable differences in form. In this way, each volcano develops a unique character shaped by its internal conditions. Some volcanoes collapse inward after major eruptions, forming wide depressions called calderas. These collapses occur when a magma chamber empties significantly and the ground above can no longer support its own weight. Later eruptions may partially refill the depression, creating new peaks within old boundaries. The mountain continues its slow evolution. Submarine volcanoes follow similar patterns beneath the sea. Lava meeting water cools quickly, forming rounded shapes known as pillow lavas. Layer upon layer accumulates until, in some cases, the volcano rises above sea level to become an island. Even then, the building process continues, sometimes accompanied by erosion from waves and storms. Volcanic mountains are therefore dynamic structures shaped by addition and subtraction, by flow and cooling, by pressure and release. They are never truly finished. Even dormant volcanoes retain the memory of past activity within their layered interiors. As you rest with this image, consider how repetition builds strength. A single eruption may seem powerful, but it is the steady pattern of many that creates a mountain. The architecture of volcanoes reflects patience more than force. In the quiet intervals between eruptions, weathering and life begin their gentle influence. Soil forms slowly from broken rock. Seeds find purchase in small crevices. The once bare slopes begin to soften with green. The mountain stands as both a monument to fire and a cradle for renewal. In the next chapter, we will move closer to the flowing lava itself, tracing how molten rock travels across the land, cools into intricate textures, and leaves behind patterns that reveal the hidden motion beneath the surface. When lava first reaches the open air, it does not always arrive in a burst of noise. Often, it emerges as a steady glow, spilling from a vent and beginning its slow descent across the land. You can imagine it moving like thick honey poured onto cool stone, bright at its core and darker at its edges. The Earth is not shouting in this moment. It is simply allowing warmth to travel outward. Lava is magma that has reached the surface. Once exposed to the atmosphere, it begins to lose heat immediately. The outer layer cools first, forming a thin crust that floats upon the still molten interior. Beneath that crust, liquid rock continues to flow, insulated by its own hardened shell. This delicate balance between cooling and movement shapes the textures you later see preserved in stone. The speed at which lava moves depends largely on its viscosity, a measure of how resistant it is to flowing. Lava with lower silica content tends to be less viscous. It spreads more easily, forming long rivers that can travel many kilometers before solidifying. In places like oceanic islands, these basaltic flows create wide expanses of dark rock that stretch toward the sea. Higher silica lava behaves differently. It is thicker, more resistant, moving with reluctance. Instead of forming smooth rivers, it may pile up near the vent, creating domes or short, stubby flows. The difference lies in the microscopic structure of the molten material. Silica forms interconnected chains within the melt, increasing its resistance to motion. What appears simple at the surface is shaped by chemistry deep within. Temperature also guides the journey. Hotter lava is generally less viscous, allowing it to move more freely. As it cools, crystals begin to form within it, increasing its thickness. Each degree of temperature change subtly alters the flow. You might picture the lava's path as a conversation between heat and gravity, each influencing how far the molten rock will travel. On gentle slopes, fluid lava can create smooth, ropey textures known as pa-ho-ho. These surfaces look almost like folded fabric or twisted cords, are formed as the still-moving lava beneath wrinkles the cooling crust above. On steeper slopes or with slightly cooler lava, rougher textures develop, broken and jagged, known as AAR. Both types tell a story of motion slowed by cooling. As lava advances, it interacts with the landscape. It may follow existing valleys, filling them like glowing streams. It can encounter forests, rivers, or older rock formations, flowing around obstacles when possible. If it meets water, rapid cooling occurs, producing steam and fragmenting the lava into small pieces. In the ocean, this interaction creates rounded pillow shapes, each one forming as lava pushes outward into cold seawater and solidifies almost instantly. Gases dissolved in lava escape gradually as pressure decreases. Bubbles rise through the molten material, sometimes becoming trapped as the lava solidifies. These trapped bubbles create vesicles, small cavities that lighten the rock and give it a porous texture. Over time, minerals may fill these spaces, forming delicate crystals inside once hollow pockets. Sleep reminder here. Let your breath move slowly, like lava finding its path down a quiet slope. There is nothing you need to hold tightly. Just allow the image of warmth becoming stone to settle gently in your mind. As lava cools further, minerals crystallize in predictable sequences depending on temperature and composition. Dark minerals rich in iron and magnesium tend to form first in basaltic lava. Lighter minerals may appear later as cooling continues. The size of the crystals depends on how quickly the lava loses heat. Rapid cooling produces fine-grained rock. sometimes even volcanic glass, smooth and reflective. One of the most striking examples of rapid cooling is obsidian, a natural volcanic glass formed when silica-rich lava cools so quickly that crystals cannot form. Its surface can appear glossy and smooth, reflecting light like polished stone. Though it begins as glowing liquid, it ends as something cool and dark, holding within it the memory of intense heat. Over days, weeks, or months, an active flow gradually loses its brightness. The red glow dims to black, steam fades. What remains is a hardened landscape, sometimes cracked and uneven, sometimes gently curved. Yet beneath that still surface, residual heat may linger for years. The rock continues to adjust internally as it cools completely. Lava does not always move in open air. Sometimes it forms tubes. As the outer surface of a flow cools and solidifies, molten lava can continue traveling beneath, carving a hollow channel. When the supply diminishes, the molten interior drains away, leaving behind a long, empty tunnel. These lava tubes may later shelter plants and animals, even people, protected from weather above. The thickness of a lava flow varies. Some flows are only a few meters deep, while others accumulate in thicker layers. Repeated flows can stack upon one another, gradually elevating the terrain. In this way, motion becomes structure. What was once fluid becomes foundation. Gravity guides every movement. Lava always seeks lower ground, flowing downhill, spreading outward. Yet its path is never perfectly straight. Subtle variations in slope, surface roughness, and internal temperature create branching channels and overlapping lobes. Each flow leaves a signature pattern, frozen in time. Over long periods, weathering begins to soften these surfaces. Rainwater seeps into cracks, expanding and contracting with temperature changes. Plants anchor roots in small crevices. The once harsh landscape slowly becomes habitable. The transformation from glowing river to quiet ground unfolds without hurry. As you rest with this image, consider how movement shapes the world around you. Lava does not rush to become stone. It cools gradually, allowing textures to form, minerals to crystallize, shapes to emerge. The Earth's motion is patient, deliberate, guided by simple physical principles acting over time. In the next chapter, we will lift our gaze from the flowing ground to the sky above, where ash and fine particles drift gently through the atmosphere, coloring sunsets and traveling far beyond the mountain slopes. When a volcano releases ash into the sky, it does not always do so in fury. Sometimes the movement is soft, almost graceful, as a pale plume rises and unfolds above the mountain. You can imagine it lifting like a slow exhale, carrying fine particles upward into layers of air you rarely think about. The ash is not smoke, though it may look similar from a distance. It is made of tiny fragments of rock and volcanic glass, shattered during eruption and carried skyward by expanding gases. These particles vary in size. Some are coarse and fall back to the ground quickly, settling on slopes and nearby valleys. Others are so fine that they remain suspended in the atmosphere, light enough to drift on upper winds. When eruptions are strong enough to push ash high into the stratosphere, the particles can circle the globe, traveling quietly above clouds and continents. Ash forms when gas-rich magma breaks apart as pressure drops suddenly near the surface. The molten material fragments into sharp-edged pieces that cool rapidly in the air. Though the process can be energetic, the journey that follows is often gentle. High-altitude winds guide the ash far from its source, dispersing it in thin veils. In the atmosphere, these particles interact with sunlight. Tiny droplets of sulfur dioxide released during eruptions can combine with water vapor to form sulfate aerosols. These aerosols scatter sunlight, reflecting a portion of it back into space. When enough of them gather high in the atmosphere, they can contribute to temporary cooling at the surface. The effect is subtle, measured across months or years, not moments. You might picture the sky as a vast ocean of air. Ash becomes like drifting sediment within that ocean, moving along invisible currents. Over time, gravity draws it downward. Gentle rains can wash particles from the air, carrying them back to the surface. What began as molten rock becomes dust that nourishes soil. On the ground, ash can blanket landscapes in soft layers. Though it may seem barren at first, volcanic ash often contains minerals that enrich the earth as it weathers. Over seasons and years, rain and microbial activity break down the particles, releasing nutrients that support plant growth. In this way, ash contributes quietly to fertility. When ash spreads across distant regions, it sometimes creates spectacular sunsets. The fine particles in the upper atmosphere scatter shorter wavelengths of light, allowing deeper reds and oranges to glow more intensely at dusk. People thousands of kilometers away may admire a vivid sky without knowing that a distant volcano has shaped the colors they see. The height of a volcanic plume depends on the force of eruption and atmospheric conditions. Warm rising gases create buoyant columns that carry ash upward. As the plume ascends, it cools and spreads outward, often forming a shape reminiscent of a towering cloud. Eventually, gravity and wind begin to disperse it. Not all ash travels far. Heavier fragments fall quickly, sometimes while still warm, landing near the vent. Over repeated eruptions, layers of ash accumulate around the volcano, compacting into rock known as tuff. These layers preserve a record of past events, with each one marking a moment when stone briefly became airborne. In aviation, ash clouds are monitored carefully because fine particles can damage aircraft engines. Satellites track plumes from space, observing their spread across regions. These observations allow scientists to predict where ash may travel, ensuring safety for those moving beneath the sky. Sleep reminder here. Let your thoughts drift like fine ash on a high current of air. There is nothing you need to control. Just allow the image of a quiet plume dissolving into wide blue space. Volcanic gases contribute not only to cooling, but also to the long-term cycling of elements. Sulfur compounds eventually settle and integrate into ecosystems. Carbon dioxide released during eruptions becomes part of the broader carbon cycle, exchanged between atmosphere, ocean, and land over time. Rain interacting with volcanic gases can produce acidic precipitation near eruption sites. This process alters soils and rocks, accelerating chemical weathering. Though the immediate effects may seem harsh, ecosystems often adapt. Over time, landscapes transform, balancing new conditions. Ash particles, when examined under microscopes, reveal angular shapes and delicate textures formed during rapid cooling. These shapes influence how particles scatter light and how they settle. Even at the smallest scale, the story remains one of transformation from molten to solid. High-altitude plumes can sometimes generate their own lightning. As ash particles collide within turbulent clouds, static electricity builds and discharges. Yet even this dramatic spark exists within a larger pattern of atmospheric movement that soon calms and disperses. As the ash finally settles, it merges with soil, water, and stone. What once floated high above continents becomes part of riverbeds or farmland. The sky clears. The memory of the plume lingers only in rock layers and perhaps in stories told by those who watched it rise. You may notice how this chapter lifts your gaze upward, from the solid ground to the open sky. The Earth's inner warmth not only builds mountains and shapes land, but also reaches into the atmosphere, touching weather and light itself. In the next chapter, we will follow that warmth even farther, beyond coastlines and into the depths of the ocean, where new islands quietly rise from beneath the waves. Far beneath the surface of the ocean, where sunlight fades into deep blue and pressure grows steady and immense, the Earth continues its quiet work. You might imagine the sea floor as flat and silent, but it is alive with slow geological motion. Here, underwater volcanoes rise from cracks in the crust, building new land grain by grain in darkness. From warmth beneath waves, new ground appears. At mid-ocean ridges, tectonic plates drift gently apart. As they separate, magma rises to fill the gap. When this molten rock meets the cold seawater, it cools almost instantly, forming rounded shapes known as pillow lava. Each pillow begins as a small bulge of lava pushing outward, its surface solidifying quickly while molten rock continues to inflate it from within. Layer upon layer of these rounded forms stack together, creating new oceanic crust. This process unfolds continuously along thousands of kilometers of underwater ridges. The sea floor spreads slowly, at a pace similar to the growth of your fingernails. What feels permanent beneath the ocean is in fact freshly formed in geological terms. The crust beneath the deepest waters is younger near these ridges and grows older as it drifts away. Sometimes volcanic activity beneath the sea becomes vigorous enough to build upward toward the surface. Repeated eruptions add more material, slowly raising a mountain from the ocean floor. Most of these submarine volcanoes never reach the air. They remain hidden beneath kilometers of water. But in some places, patience and persistence lift the peak above sea level, and an island is born. When a new island emerges, it often begins as dark, barren rocks surrounded by waves. Steam may rise where hot lava meets seawater. The shoreline is rough and unstable at first, shaped by cooling flows and shifting fragments. Yet even here, life waits quietly. Seabirds may rest upon the new ground. Wind carries seeds. Salt-tolerant plants find small crevices where moisture gathers. The chemistry of underwater eruptions differs slightly from those on land. The immense pressure of deep water suppresses the violent expansion of gases within magma. As a result, eruptions at great depths are often less explosive. Lava flows more calmly, spreading along the seafloor. The ocean absorbs much of the heat, cooling the lava rapidly and shaping it into distinctive forms. Hydrothermal vents often accompany these volcanic systems. As seawater seeps into cracks in the hot crust, it heats, dissolving minerals from the surrounding rock. The superheated water then rises back through the seafloor, emerging as dark plumes, rich in dissolved metals and chemicals. These vents create mineral deposits that accumulate like chimneys on the ocean floor. Around these vents, life flourishes in unexpected ways. Microorganisms use chemical energy from vent fluids rather than sunlight to survive. Larger organisms, such as tube worms and specialized crustaceans, depend on these microbes. In the deep darkness, Warmth and chemistry replace light as the foundation of ecosystems. It is a quiet reminder that volcanic heat supports life even in places untouched by the sun. Some island chains form not at plate boundaries, but above mantle plumes. These plumes rise from deep within the earth, delivering steady heat to the base of the crust. As a tectonic plate moves slowly over a relatively fixed plume, volcanoes form one after another along its path. The result is a chain of islands arranged like stepping stones across the ocean. In such chains, the youngest island sits above the active plume, while older islands drift away as the plate moves. Over time, erosion wears down the older islands. Waves carve cliffs. Rain softens slopes. Eventually, some islands subside below sea level, leaving only coral reefs or submerged seamounts as reminders of their fiery origins. Sleep reminder here. Let your breathing become steady, like the slow spreading of the ocean floor. There is nothing you need to hold on to. Just picture new land rising patiently beneath wide blue waters. The cooling of submarine lava often traps seawater within cracks and cavities. As the rock solidifies, these trapped fluids may alter the surrounding minerals through chemical reactions. This process changes the composition of the crust, integrating elements from both earth and ocean. Underwater eruptions can also create explosive interactions when lava encounters shallow water. Steam forms rapidly, fragmenting lava into fine particles. These fragments may settle to the seafloor, or if the eruption reaches near the surface, rise into the air as ash. Even here, the ocean moderates much of the force, absorbing energy and dispersing heat. Over long periods, volcanic islands may grow large enough to support forests, rivers, and human communities. Their soils are often fertile, enriched by minerals from weathered basalt. Rainfall on volcanic slopes can create lush vegetation, transforming once barren rock into green landscapes. Yet beneath these peaceful scenes, the mantle plume or spreading ridge continues its slow work. Heat rises, magma forms. The cycle does not rush. It unfolds over millions of years, shaping ocean basins and continents alike. You may find comfort in the idea that even in the deepest darkness, beneath crushing pressure and far from sunlight, the Earth is building quietly. Islands do not appear overnight. They rise through repetition, through steady pulses of heat meeting cold water. In the next chapter, we will trace one of the great arcs of volcanic activity that circles the Pacific Ocean, where plates converge in a broad, patient ring of fire-shaping coastlines and mountain ranges across vast distances. If you were to trace a slow line around the edges of the Pacific Ocean, moving from the western coasts of the Americas, curving northward toward Alaska, sweeping across Japan, down through Southeast Asia, and along toward New Zealand, you would outline a vast arc where volcanoes gather. This arc is often called the Ring of Fire, yet the name can sound more dramatic than the reality. What truly exists there is not chaos, but steady motion. A circle shaped by balance and pressure, by plates meeting and adjusting over immense spans of time. Beneath the Pacific Basin, tectonic plates are in constant, gradual movement. They drift only a few centimeters each year, almost too slowly to notice within a lifetime. But when one plate moves toward another, something gentle yet powerful unfolds beneath the surface. At many points along this arc, an oceanic plate bends and slides beneath a neighboring plate, descending into the mantle. This process is called subduction, though you do not need to remember the term. You can simply picture one broad slab of crust easing beneath another like a slow, steady bow. As the descending plate sinks deeper, it carries with it water trapped in minerals and sediments. With increasing depth and temperature, this water is released into the overlying mantle. The presence of water lowers the melting point of the surrounding rock, encouraging pockets of magma to form. This magma begins its upward journey, rising through the crust, eventually feeding volcanoes that appear along the surface. Because so many subduction zones border the Pacific Ocean, volcanoes gather in this wide ring. The Andes in South America, the Cascades in North America, the volcanic arcs of Japan and the Philippines, and many others all share this underlying pattern. Though they stand in different climates and cultures, their origin is connected by the same quiet mechanics beneath the crust. Earthquakes are also common along these boundaries. As plates press and grind past each other, stress builds slowly. When that stress releases, the ground may tremble. Yet even these movements reflect accumulated pressure over years or centuries. The Earth is adjusting itself, redistributing energy as plates settle into new positions. The volcanic mountains along this ring are often steep and layered. The magma generated in subduction zones tends to contain higher amounts of silica, making it more viscous. This thicker magma can trap gases more easily, leading to explosive eruptions at times. But even here, the dramatic moments are brief compared to the long intervals of quiet between them. You might imagine the Pacific Ocean as a great bowl surrounded by rising edges. Along those edges, continents and islands lift gradually, shaped by repeated eruptions and tectonic uplift. The ocean floor itself is in motion, spreading outward from mid-ocean ridges and eventually descending again at subduction zones. It is a slow cycle of creation and return. The trenches that mark subduction zones are among the deepest places on Earth. These long, narrow depressions form where the oceanic plate bends downward. They remind you that even the solid crust can curve and descend under pressure. Far below, the sinking slab continues its journey into the mantle, gradually blending with the surrounding material. Volcanic arcs formed by subduction often align in graceful curves. These arcs mirror the shape of the descending plate boundary. Islands like those of Japan or Indonesia sit above these zones, each volcano connected invisibly to the same descending slab far beneath the ocean floor. Not all movement along the Ring of Fire involves one plate diving beneath another. In some regions, plates slide past each other horizontally. These transform boundaries do not typically create volcanoes, but they still release built-up stress in the form of earthquakes. The ring, therefore, is a mosaic of different boundary types, each contributing to the overall pattern. Sleep reminder here. Let your thoughts circle gently, like the arc around the Pacific. There is nothing you need to trace precisely. Just sense the wide curve of continents meeting ocean, of plates adjusting in slow harmony. Volcanic soils along this arc are often fertile, enriched by minerals from weathered lava and ash. Many dense human populations live along these coasts, farming on land shaped by past eruptions. Mountains that once glowed now support forests, villages, and cities. Life and geology intertwine in quiet continuity. The movement of plates around the Pacific is part of a larger global network. The lithosphere is divided into several major plates and many smaller ones. Their interactions define not only volcanoes, but also mountain ranges and ocean basins worldwide. The Ring of Fire is simply one visible expression of a deeper planetary rhythm. Deep beneath the surface, the descending slabs can influence mantle flow patterns. Seismic studies reveal that some slabs sink far into the mantle before warming and blending with surrounding material. The heat that drives this circulation ultimately comes from Earth's interior, from processes ongoing since the planet formed. You may find it calming to realize that what seems dramatic from the surface is governed by consistent physical principles. Pressure, temperature, density, and gravity guide every movement. There is no hurry in these adjustments. The ring does not burn continuously. It pulses gently over geological time. As you rest with this wide image of Earth's largest ocean framed by mountains and volcanoes, consider how balance arises from motion. Plates converge and separate, descend and rise. Through these interactions, landscapes are renewed. In the next chapter, we will slow our pace even further and consider the immense scale of certain volcanic systems, where entire regions rise and fall over deep time, shaping climates and continents in ways that unfold beyond a single human lifetime. There are places on Earth where the volcanic story grows so wide that it no longer looks like a single mountain. Instead of a pointed peak rising against the sky, you find a broad landscape, rolling and forested, with lakes and meadows resting quietly above something immense. Beneath these calm surfaces lie some of the largest volcanic systems on the planet, shaped not by one eruption, but by events so vast and so distant in time that they stretch your imagination gently outward. These systems are often marked by calderas, large depressions formed when an enormous volume of magma empties from beneath the surface and the ground above slowly collapses inward. The collapse is not like a sudden sinkhole in the quiet of night. It is the surface adjusting to the loss of support below, settling into a new shape. What remains can span tens of kilometers, wide enough to hold rivers, forests, and entire ecosystems within its rim. One well-known example rests in North America, where a broad plateau sits above a deep magmatic system. At the surface, you see geysers, hot springs, and gently rising steam. Beneath that serene landscape lies a complex network of partially molten rock and solidified intrusions. The heat from below warms groundwater, creating hydrothermal features that whisper rather than roar. Supervolcanic eruptions in the distant past released enormous volumes of ash and lava across wide regions. The ash traveled far, settling over continents in fine layers. Over time, these layers compacted into rock, preserving a memory of that ancient event. Yet even these powerful eruptions are rare when viewed across millions of years. Most of the time, these systems remain quiet, circulating heat slowly beneath the crust. The magma chambers associated with such systems are not single empty caverns filled with glowing liquid. They are complex zones where partially molten rock mixes with solid crystals. Magma accumulates gradually, replenished by deeper sources over long intervals. Cooling, crystallization, and mixing all occur within these hidden reservoirs, shaping the chemistry of future eruptions. When large eruptions occur, they can influence climate for a time. Fine particles and sulfur compounds injected high into the atmosphere may reflect sunlight, contributing to temporary cooling at the surface. Historical records and geological evidence reveal periods when global temperatures dipped slightly after major volcanic events. These shifts unfold over years, not moments, and gradually fade as particles settle from the atmosphere. Sleep reminder here. Let your thoughts stretch into deep time. There is nothing you need to calculate. Just imagine centuries passing, like quiet pages turning in a very long book. The landscape within a caldera often evolves after collapse. New lava domes may rise slowly from the floor, filling portions of the depression. Lakes may form where drainage patterns adjust. Vegetation returns, taking root in fertile volcanic soils enriched by mineral deposits. What was once the site of immense energy becomes a place of calm beauty. Our geophysical monitoring today allows scientists to measure subtle changes in these systems. Ground may rise or fall slightly as magma moves below. Seismic waves reveal patterns of rock and melt beneath the surface. Heat flow measurements trace the movement of thermal energy upward. These observations do not indicate constant unrest. Rather, they reveal a living system adjusting gradually over time. The concept of deep time becomes especially clear when you consider how infrequently supervolcanic eruptions occur. Between major events, tens or hundreds of thousands of years may pass. During those intervals, glaciers advance and retreat, species evolve, rivers carve new paths. Human history occupies only a tiny fraction of that span. Beneath the surface, heat continues its patient circulation. Mantle plumes or other deep processes feed these systems with energy from Earth's interior. The crust above flexes and responds, sometimes fracturing, sometimes sealing again. It is a dialogue between layers of rock carried out in silence. Even the mineral crystals formed within cooling magma record the history of these systems. Zoned crystals preserve evidence of temperature shifts and mixing events, like tree rings capturing seasons. By studying them, scientists piece together the slow evolution of magma chambers over millennia. The scale of these systems can feel overwhelming, yet their processes are governed by the same physical principles as smaller volcanoes. Pressure, temperature, density, and composition determine how magma behaves. The difference lies primarily in volume and duration. The timescales expand, the chambers widen, but the fundamental mechanics remain steady. You may notice how thinking about deep time softens urgency. When you picture landscapes evolving over hundreds of thousands of years, your own concerns can feel lighter. There is nothing you need to solve tonight. The Earth has been adjusting itself long before your first breath and will continue long after. Hydrothermal features within large calderas provide windows into the heat below. Water heated by underlying magma rises to the surface, sometimes erupting gently as geysers when pressure builds within underground channels. Mineral-rich waters deposit colorful terraces as they cool. These patterns are delicate reminders of the immense system hidden beneath. Over vast spans, erosion gradually reshapes caldera rims. Rivers cut through edges, carrying sediment away. Tectonic uplift or subsidence may alter the elevation of the entire region. The landscape you see today is only one chapter in an ongoing story. As you rest with this wide perspective, imagine standing within such a caldera, unaware at first that you are inside the remnant of an ancient eruption. Meadows stretch before you. Steam rises quietly in the distance. Beneath your feet lies a history, measured not in years, but in epochs. In the next chapter, We will turn from these immense systems to consider how volcanoes contribute to the very air and oceans around you, shaping atmospheres and cycles that touch every living thing. When you imagine a volcano, you may picture flowing lava or rising ash. Yet, long before lava glows or ash drifts across the sky, something more subtle is happening. Invisible gases rise quietly from molten rock, escaping through vents and fractures in the crust. In this way, volcanoes breathe, not in quick, shallow bursts, but in deep planetary exhales that have shaped the air and oceans over vast stretches of time. Deep beneath the surface, magma holds dissolved gases under immense pressure. Water vapor, carbon dioxide, sulfur compounds, and smaller amounts of other gases remain mixed within the molten rock, compressed by the weight of layers above. As magma rises and pressure decreases, these gases begin to separate from the melt. They form bubbles that expand, sometimes driving eruptions, sometimes escaping gently through cracks without dramatic display. Water vapor is often the most abundant volcanic gas. In Earth's distant past, when the planet was far hotter and its surface still cooling, a repeated volcanic outgassing released vast quantities of steam into the atmosphere. Over time, as the surface cooled sufficiently, that steam condensed, falling as rain. For millions of years, rain fell and fell again, collecting in low places and gradually forming the early oceans. In this way, volcanic breath contributed to the waters that now cover much of the planet. Carbon dioxide, another common volcanic gas, plays its own role. It absorbs heat in the atmosphere, helping regulate temperature through the greenhouse effect. In Earth's early history, when the sun shone less brightly than it does today, higher concentrations of carbon dioxide likely helped keep the planet warm enough for liquid water to persist. The balance was delicate, shaped by interactions between volcanic emissions, weathering of rocks, and absorption by oceans. Sulfur gases released during eruptions can transform in the atmosphere, forming tiny sulfate particles. These particles reflect a portion of incoming sunlight back into space, sometimes leading to temporary cooling at the surface. Such effects may last months or a few years before particles settle and conditions return to previous patterns. The atmosphere adjusts, absorbing and redistributing the influence of each volcanic exhale. Volcanoes also release smaller amounts of nitrogen, hydrogen, and trace elements. Each gas joins larger cycles that move between land, sea, and air. Nothing remains isolated for long. Carbon released from magma may dissolve into ocean water, become incorporated into marine organisms, and eventually settle into sedimentary rock. Over geological time, tectonic processes can return that carbon to the mantle, completing a slow loop. You might think of these cycles as vast circulatory systems. Volcanoes provide one pathway by which materials from deep within Earth reach the surface. Rain, rivers, and chemical reactions in soils provide another, drawing elements back toward the ocean or into rock. The planet maintains its atmosphere not as a fixed shell, but as a dynamic balance shaped by many processes working together. Sleep reminder here. Let your breath mirror the planet's own rhythm. Inhale slowly, exhale gently. There is nothing you need to measure. The Earth's breathing has unfolded for billions of years without hurry. In regions with active volcanoes, you may notice fumaroles, openings where gases escape steadily from the ground. These vents release steam and sulfur compounds that create distinct mineral deposits around them. Over time, Minerals crystallize from cooling gases, painting rocks in yellows, whites, and reds. Even these small vents are part of the broader exchange between interior and atmosphere. Hydrothermal systems, warmed by underlying magma, also contribute gases to the air and dissolved compounds to water. As groundwater circulates through hot rock, it absorbs heat and minerals before rising again. The boundary between volcanic gas and heated water becomes blurred, both carrying signatures of Earth's internal chemistry. On a global scale, the rate of volcanic gas release is modest compared to human industrial emissions today. Yet, over geological time, volcanic activity has been a primary source of atmospheric carbon dioxide. Without it, much of the carbon now cycling through air and ocean might remain locked deep within the mantle. The interplay between volcanic emissions and weathering processes helps stabilize long-term climate. When carbon dioxide levels rise, chemical weathering of rocks tends to increase, drawing carbon back out of the atmosphere and storing it in carbonate minerals. These minerals may eventually be subducted, returning carbon to the mantle. It is a feedback loop spanning millions of years. Early in Earth's history, volcanic gases likely included significant amounts of methane and ammonia as well. The exact composition of the early atmosphere remains a subject of research, but volcanic outgassing clearly played a foundational role. The air you breathe tonight is the result of countless such contributions, modified over time by life itself. Photosynthetic organisms eventually altered the atmosphere dramatically, increasing oxygen levels. Now, yet even oxygen's story is indirectly connected to volcanic processes, because the nutrients and minerals required by early life were supplied in part by volcanic rock and hydrothermal activity. You may find it soothing to realize that the air surrounding you is not static. It is part of a vast exchange linking deep magma chambers, ocean currents, forests, and clouds. Volcanoes do not simply build mountains. They help sustain the cycles that make life possible. Even on other planets and moons, volcanic gases shape atmospheres. On worlds without active volcanism, atmospheres may thin over time as gases escape into space. On those with ongoing activity, fresh gases replenish what is lost. Earth's persistent internal heat has allowed its atmosphere to endure. As you rest with this image of a breathing planet, imagine the slow rise of invisible gases from warm rock to open sky. Consider how rain, ocean, and stone respond in turn, maintaining a balance that has lasted for ages. In the next chapter, we will turn our attention to the living world that returns after eruptions, exploring how plants and animals gradually reclaim volcanic landscapes and transform ash and lava into thriving ecosystems. When the lava finally cools and the red glow fades to black, the landscape can seem still and empty. The rock is sharp in places, smooth in others, patterned with ropes and ridges where molten currents once flowed. At first glance, it may appear lifeless. Yet even in this quiet, life is already preparing its return. Renewal does not hurry, but it does not hesitate either. Fresh basalt, newly formed from cooling lava, is rich in minerals such as iron, there's magnesium, and calcium. These elements are locked within the crystal structure of the rock. Over time, wind, rain, and changes in temperature begin to break the rock down. Tiny fractures widen. Water seeps into cracks and expands as it freezes, gently prying stone apart. What begins as solid lava gradually crumbles into smaller fragments. The first living organisms to settle on bare volcanic rock are often microscopic. Bacteria and fungi arrive carried by air and water. Some of them are capable of surviving in harsh conditions, drawing energy from chemical reactions within the minerals themselves. They form thin films across the surface, invisible at first, but essential in preparing the ground for what comes next. Lichens are among the earliest visible pioneers. These remarkable organisms are partnerships between fungi and photosynthetic algae or cyanobacteria. The fungal component anchors to rock and absorbs moisture, while the photosynthetic partner captures sunlight to produce energy. Together, they slowly release acids that help break down minerals in the rock. Over years and decades, this process contributes to the formation of the first thin layer of soil. Mosses often follow. They do not require deep soil to grow. Instead, they anchor in tiny crevices where dust and organic matter collect. Mosses trap moisture and add their own decaying material to the developing soil. Each small plant contributes a little more organic matter, thickening the fragile layer atop the basalt. Sleep reminder here. Imagine a quiet black field of cooled lava beneath a gentle rain. There is nothing you need to do. Just allow the image of green returning slowly to settle in your mind. As soil deepens, grasses and small flowering plants find places to root. Seeds arrive carried by wind, birds, or ocean currents if the volcano stands near the sea. Some seeds remain dormant until conditions are right. Others sprout quickly when moisture and nutrients align. The once barren surface begins to soften under patches of green. Insects arrive soon after plants. They feed on leaves, burrow into soil, and pollinate flowers. Their presence attracts birds, which bring additional seeds and nutrients. Each step builds upon the last, creating a web of life from what once appeared empty. Volcanic ash, when weathered, can be especially fertile. Though it begins as fine fragments of rock and glass, rain and microbial activity transform it into soil rich in nutrients. Regions surrounding volcanoes often support productive forests and agriculture because of this mineral abundance. The very material that once drifted through the sky becomes the foundation for thriving ecosystems. On islands formed by volcanic activity, this process of ecological succession unfolds in relative isolation. The first colonizers must travel across open ocean, carried by wind or resting on floating debris. Over time, these islands may develop unique communities of plants and animals, shaped by both volcanic origin and geographic separation. In tropical climates, vegetation can return rapidly, sometimes within a few years of an eruption. In colder regions, the process may take much longer. Climate, rainfall, and elevation all influence the pace of recovery. Yet the direction remains the same. A life moves gradually back into spaces shaped by fire. As forests mature on volcanic slopes, roots penetrate deeper into the soil, stabilizing the ground. Fallen leaves accumulate, creating rich layers of humus. Streams carve channels through softened rock, carrying nutrients downhill. What was once a stark landscape becomes textured with shade and sound. Some species are especially adapted to volcanic environments. Certain plants tolerate mineral-rich soils that might challenge others. Some animals exploit newly opened habitats free from established competitors. In this way, eruptions can reset ecological communities, creating opportunities for change and diversification. The transformation from lava field to forest can take centuries. Yet from the perspective of geological time, even centuries are brief. The mountain stands quietly as life weaves itself across its slopes, responding to warmth stored deep below and minerals released at the surface. Volcanic landscapes also preserve a memory of past life beneath newer growth. Layers of ash may entomb plants and animals, protecting their forms within hardened rock. Over long periods, these preserved traces become fossils, offering glimpses into ecosystems that existed before or between eruptions. You may find comfort in knowing that renewal is woven into Earth's processes. Fire does not hold the final word. After heat comes cooling. After cooling comes soil. After soil comes green life rising towards sunlight. Even human communities often return to volcanic regions after eruptions. Fertile soils and access to water draw people back. Villages rebuild. Crops grow. The relationship between volcano and life becomes one of coexistence rather than opposition. As you rest with this gentle cycle of destruction and renewal, imagine the quiet persistence of moss spreading across cooled stone. Feel the patience of roots exploring newly formed soil. Life waits, but it also advances steadily when conditions allow. In the next chapter, we will turn our attention to the ways human cultures have lived beside these fire-shaped mountains, learning to read their signs and weaving volcanic landscapes into stories, traditions, and daily life. Long before satellites traced ash clouds from space, before seismographs listened to the faint tremble of rising magma, people lived in the shadow of volcanoes and learned their rhythms by watching the land itself. You can imagine a village at the foot of a mountain, fields stretching across dark, fertile soil, smoke rising gently from cooking fires, while, far in the distance, a thin plume curls from the summit. The mountain is not only a threat, it is also a provider. Volcanic soils formed from weathered ash and lava often hold abundant minerals. Farmers have long noticed that crops grow well in these regions. Grains, fruits, and vegetables draw nourishment from elements released as basalt and ash break down over time. In many parts of the world, dense populations have settled near volcanoes, not despite their presence, but partly because of the fertility they offer. In ancient Italy, the city of Pompeii stood near Mount Vesuvius. For centuries, the mountain appeared quiet, its slopes supporting vineyards and orchards. When it erupted in the 1st century, ash and pumice buried the city rapidly, and preserving buildings and everyday objects beneath layers of volcanic material. Today, those preserved streets provide a detailed glimpse into Roman life. The eruption was tragic, yet the ash that caused destruction also became a record, holding history within stone. Across the Pacific, Mount Fuji rises with graceful symmetry above Japan. For generations, it has been both a geological presence and a cultural symbol. Artists have painted it. Poets have written of its snow-capped peak. Though it is a stratovolcano shaped by repeated eruptions in the distant past, it now stands in long quiet, its slopes visited by hikers and pilgrims seeking perspective. The mountain reminds you that volcanic landscapes can become places of reflection. In Hawaii, volcanic activity continues to shape land and tradition, as the islands themselves were formed by lava rising from a mantle plume beneath the Pacific Plate. Indigenous Hawaiian culture includes deep respect for volcanic forces, expressed through stories and practices that acknowledge the living land. While scientific understanding explains magma and tectonics, cultural narratives offer meaning and connection, weaving geology into identity. Sleep reminder here. Let your thoughts drift across continents and centuries. There is nothing you need to judge or resolve. Just notice how people and mountains share space in quiet coexistence. Throughout history, communities near volcanoes have developed ways to read subtle signs. Changes in the smell of air, small earthquakes, unusual animal behavior, or new steam vents might signal activity. Without modern instruments, observation and memory were essential tools. Knowledge passed through generations helped people respond when the mountains stirred. In Indonesia, where many volcanoes line the archipelago, rice terraces climb fertile slopes shaped by past eruptions. Temples and villages stand amid landscapes that owe their form to lava and ash. The relationship between people and volcanoes here is ongoing, shaped by adaptation and resilience. In parts of Central and South America, civilizations such as the Maya and Inca lived among volcanic peaks. They built cities, cultivated crops, and incorporated nearby mountains into spiritual worldviews. The Andes, formed by subduction along the Pacific margin, host numerous volcanoes that rise above high plateaus. Human life unfolded alongside tectonic motion. Modern science has deepened understanding of volcanic systems, but the human experience remains similar in one way. Living near a volcano requires awareness of both risk and benefit. Monitoring networks now measure ground deformation, gas emissions, and seismic patterns. Early warning systems allow evacuation when necessary. The goal is coexistence informed by knowledge. Volcanic materials have also been used in construction. In ancient Rome, volcanic ash mixed with lime and water created a durable concrete that still supports structures today. Pumice, a lightweight volcanic rock filled with trapped gas bubbles, has served as an abrasive and building material. Even obsidian, formed from rapidly cooled lava, was shaped into sharp tools and decorative objects in many cultures. Art and literature often reflect the presence of volcanoes. Writers describe distant plumes against twilight skies. Painters capture glowing lava under dark clouds. These artistic expressions transform geological processes into symbols of endurance, transformation, and renewal. Despite occasional eruptions, many volcanoes remain dormant for centuries. Generations grow up knowing the mountain only as a backdrop, its slopes part of everyday life. Children play in fields nourished by past eruptions, unaware of the deep magma chambers below. Life continues with a quiet trust in monitoring and collective memory. You may notice how human stories around volcanoes are not solely about fear. They are about adaptation, reverence, and continuity. People plant seeds in fertile soil, build homes on cooled lava, and find beauty in snow resting on once fiery peaks. Scientific study has revealed patterns in eruption frequency and magma composition, yet prediction remains complex. This uncertainty encourages humility. Communities learn preparedness while acknowledging that Earth's internal processes cannot be fully controlled. As you rest with these intertwined histories of land and life, imagine standing at the edge of a cultivated field, a mountain rising in the distance. Smoke drifts gently from its summit, barely visible against the sky. The soil beneath your feet is dark and rich, shaped by events long past. In the next chapter, we will step into the present-day methods scientists use to listen carefully to these mountains, exploring how instruments and satellites detect subtle signals that reveal movement deep below the surface. When you stand before a quiet volcano, it may appear completely still. Snow rests on its summit, trees sway gently along its slopes. From a distance, nothing seems to move. Yet beneath that calm surface, subtle signals ripple through rock and soil. Modern science has learned to listen to these quiet messages, not with urgency, but with patience. Seismographs are among the most sensitive tools used to monitor volcanoes. These instruments detect tiny vibrations within the earth, movements far too small for you to feel. When magma shifts underground, it can fracture surrounding rock or create low-frequency tremors as it moves through cracks. Each small vibration carries information about what is happening deep below. The signals are recorded continuously, creating a steady stream of data that scientists study over time. Some of these seismic signals are sharp and brief, like the snap of a branch. Others are long and rolling, like a distant hum. The pattern matters more than any single tremor. By observing changes in frequency, depth, and intensity, researchers can infer whether magma is rising, whether pressure is building, or whether the system remains in its usual state. Ground deformation is another quiet indicator. When magma accumulates beneath the surface, it can cause the ground above to swell slightly. The change may be only a few centimeters, almost imperceptible without precise measurement. Global positioning system instruments placed around a volcano can detect these small shifts. Over months or years, gradual uplift or subsidence reveals the movement of magma beneath. Satellite imaging adds another layer of observation. From space, radar instruments measure subtle changes in elevation across volcanic landscapes. By comparing repeated images, scientists can map patterns of deformation that unfold slowly over time. What appears solid and fixed to the eye is shown to be gently breathing. Gas emissions provide additional clues. Instruments near vents and fumaroles measure the composition and quantity of gases released from the ground. Increases in sulfur dioxide or carbon dioxide may signal changes in magma depth or temperature. The ratio of different gases can indicate whether fresh magma is entering a chamber or whether older material is cooling. Sleep reminder here. Let your breathing become steady, like the patient recording of instruments placed on a mountain slope. There is nothing you need to interpret. Just imagine quiet sensors listening through rock. Thermal cameras also contribute to monitoring. These devices detect heat patterns on the surface, revealing areas where temperatures rise slightly above normal. A warming crater lake or a new hotspot along a fissure can signal increased activity below. These changes are often gradual, observed over weeks or months rather than hours. Acoustic sensors sometimes capture low-frequency sounds produced by moving magma or escaping gases. Though inaudible to the human ear, these subtle vibrations can be recorded and analyzed. Even the faintest rumble becomes part of a larger picture when placed alongside seismic and gas data. Hydrological changes can also reflect volcanic activity. Rising heat may warm groundwater, altering the temperature of nearby springs. Chemical changes in water composition may signal new interactions between magma and surrounding rock. Monitoring these waters provides another gentle window into hidden processes. The key to volcanic monitoring is not a single instrument, but a network. Seismographs, GPS stations, gas analyzers, satellites, and cameras work together. Each offers one piece of the puzzle. When patterns align across multiple systems, confidence grows in understanding what is unfolding below. Prediction, in this context, is not dramatic. It is careful interpretation built on long-term observation. Scientists compare current data with historical patterns. They ask whether the present signals resemble those that preceded past eruptions. Often, changes occur without leading to eruption at all. Volcanoes adjust internally, releasing pressure gradually. Communication plays an essential role. When monitoring networks detect significant changes, authorities may raise alert levels or recommend precautions. These decisions are made thoughtfully, weighing evidence and uncertainty. The goal is not to predict every detail, but to reduce risk through preparation. You may notice how this process mirrors patience in your own life. Careful attention, steady observation, gradual understanding. There is no rush. The mountain does not reveal its intentions all at once. It speaks softly through vibrations and gases and subtle shifts. Advances in technology have deepened our ability to listen. Remote sensing allows observation of volcanoes in isolated regions. Drones can capture images and collect samples from areas too hazardous for direct access. Data flows into research centers where patterns are studied over years. Yet, even with modern tools, uncertainty remains. Volcanoes are complex systems influenced by many variables. Magma composition, chamber geometry, rock strength, and external factors all interact. Scientists continue to refine models, seeking clearer insight into how signals translate into surface events. As you imagine these quiet instruments resting along a mountainside, picture them as gentle listeners. They do not disturb the landscape. They simply record, measure, and transmit. Their purpose is awareness, not control. Monitoring efforts extend beyond active volcanoes. Dormant systems are observed as well, for they may awaken after long intervals. The Earth's interior remains warm, and its processes continue whether visible or not. You may find reassurance in knowing that many eyes and instruments watch carefully over volcanic regions today. Knowledge grows steadily, reducing surprise and increasing understanding. In the next chapter, we will widen our view beyond Earth itself, exploring how volcanic processes appear on distant planets and moons, where heat rises through alien crusts under unfamiliar skies. When you lift your gaze from Earth's mountains to the wider sky, you may wonder whether the quiet fire beneath our feet exists elsewhere. The answer, gently and steadily revealed through decades of exploration, is yes. Volcanoes are not unique to our world. Across the solar system, heat rises through crusts under different skies, shaped by different gravities and chemistries, yet guided by familiar principles. On Mars, enormous shield volcanoes rise from vast plains of basalt. The most prominent, Olympus Mons, towers far higher than any mountain on Earth. Its great height is possible partly because Mars has lower gravity and lacks the shifting tectonic plates that move crust across hotspots on our planet. Lava there could build upward in one place for millions of years, layer upon layer without drifting away. Though dormant today, its broad slopes speak of long-lived volcanic activity in the Martian past. The surface of Mars reveals channels carved by ancient lava flows. Wide plains of solidified basalt stretch across its landscape. These features suggest that Mars once possessed a warmer interior capable of generating substantial magma. Over time, as the planet cooled and its internal heat diminished, volcanic activity slowed. The red planet now holds the quiet remains of a once more active geological history. Venus, Earth's nearest planetary neighbor, also bears the marks of volcanism. Its surface is dotted with vast lava plains and numerous volcanic structures. The thick atmosphere of Venus traps heat, creating surface temperatures high enough to soften metal. Radar imaging from orbit reveals shield-like formations and extensive flow patterns. Though direct observation is challenging beneath dense clouds, evidence suggests that volcanic processes have shaped much of its terrain. Beyond the rocky planets, volcanic activity appears in more unexpected forms. Jupiter's moon Io is one of the most volcanically active bodies in the solar system. There, tidal forces from Jupiter's immense gravity stretch and compress the moon's interior. This constant flexing generates heat, melting rock, and driving eruptions that send plumes high above the surface. Io's volcanoes erupt not only molten rock, but also sulfur compounds, painting the moon in vivid hues of yellow, red, and black. Sleep reminder here. Let your thoughts drift outward, beyond Earth's blue atmosphere. There is nothing you need to grasp tightly. Just imagine warmth rising through distant worlds beneath unfamiliar stars. On Saturn's moon, Enceladus, volcanic-like activity takes a different form. Instead of molten rock, plumes of water vapor and ice erupt from fractures near its south pole. Beneath its icy crust lies a subsurface ocean warmed by tidal heating. These geysers spray material into space, creating a faint ring around Saturn. Though not volcanic in the traditional sense of molten rock, the process still reflects internal heat escaping through a crust. Even our own moon bears signs of ancient volcanism. Dark regions known as Maria are vast plains of basalt formed billions of years ago when lava filled large impact basins. The moon's smaller size allowed it to cool more rapidly than Earth, and its volcanic activity ceased long ago. Yet those smooth plains remain as quiet reminders of molten episodes in its distant past. Mercury, the innermost planet, shows evidence of volcanic plains as well. Despite extreme temperature differences between day and night, its surface preserves features consistent with ancient lava flows. As with other small rocky bodies, volcanic activity diminished as internal heat dissipated. Each world reveals variations shaped by size, composition, and gravitational influence. Yet larger planets retain heat longer, sustaining volcanic activity over extended periods. Smaller bodies cool more quickly, their volcanic chapters shorter in duration. The presence or absence of tectonic plates also influences how magma reaches the surface. The chemistry of extraterrestrial magma differs from Earth's in some cases. On Io, sulfur plays a prominent role. On icy moons, cryovolcanism involves water, ammonia, or methane erupting in frigid environments. Yet the underlying principle remains constant. Internal energy seeks release, rising through fractures and reshaping surfaces. You may notice how this shared pattern connects distant worlds. Heat trapped during planetary formation or generated through tidal forces moves upward, altering landscapes. Crusts crack, plumes rise, and material cools into new forms. The story repeats, and written in varied materials across space. Space missions equipped with cameras, spectrometers, and radar instruments have allowed scientists to identify these volcanic features from afar. Robotic explorers orbit planets and fly past moons, capturing images that reveal flow patterns, calderas, and plume deposits. Each discovery expands our understanding of how common volcanic processes are beyond Earth. The study of extraterrestrial volcanism also informs knowledge of our own planet. By comparing different worlds, scientists refine models of heat transfer, mantle convection, and crust formation. Patterns observed on Mars or Io provide context for processes unfolding beneath Earth's surface. You might find comfort in knowing that the quiet fire you have imagined beneath mountains tonight is part of a larger cosmic pattern. The solar system is not static. It is shaped by internal warmth, by gravitational interactions, by cycles of cooling and renewal. Even distant exoplanets orbiting other stars may host volcanic activity, though we cannot yet observe their surfaces directly. Clues in atmospheric composition hint at active geology beyond our solar system. The possibility extends the story further, suggesting that planetary heat is a common thread woven through the universe. As you rest with this widened perspective, picture a constellation of worlds, each with its own hidden warmth. Lava flows beneath alien skies. Ice plumes rise from frozen crusts. Mountains form and erode in silence. In the next chapter, we will return to Earth's oceans once more, are descending into the dark along mid-ocean ridges, where hydrothermal vents glow gently and life thrives without sunlight. Far below the surface of the ocean, where sunlight never reaches and the water presses with quiet, steady weight, the Earth continues its gentle exchange of heat. Along mid-ocean ridges, where tectonic plates slowly drift apart, magma rises silently from the mantle. It does not glow brightly here as it might in open air. Instead, it meets cold seawater in darkness, cooling quickly and building new crust beneath the waves. As seawater seeps down through cracks in this freshly formed crust, it journeys closer to the warmth below. The water does not boil in the way you might expect, because the immense pressure of the deep ocean raises its boiling point. Instead, it becomes superheated, absorbing minerals from the surrounding rock as it circulates through this hidden network. Eventually, the heated water rises again through fissures in the seafloor, emerging as hydrothermal vents. These vents release plumes of mineral-rich fluid into the surrounding ocean. Some appear as dark, smoky columns, not from soot, but from tiny particles of iron and sulfide minerals that precipitate as the hot water meets the cold sea. Other vents release lighter-colored plumes, rich in different dissolved minerals. Around these openings, chimney-like structures gradually form. Layer by layer, minerals accumulate as vent fluids cool and solidify. Over time, these chimneys can grow several meters tall, standing like quiet towers in the deep. In this darkness, something remarkable happens. Life gathers. There is no sunlight here to fuel photosynthesis. Instead, microorganisms harness chemical energy from the vent fluids. Through a process known as chemosynthesis, certain bacteria convert hydrogen sulfide and other chemicals into energy. These microbes form the base of an ecosystem that thrives without light. You can imagine the vents as underwater oases. Giant tube worms anchor themselves near the openings, their red plumes waving gently in the currents. These worms lack mouths and digestive systems in the way you might expect. Instead, they host symbiotic bacteria within their tissues. The bacteria perform chemosynthesis, providing nutrients to their hosts. Crabs, shrimp, and other specialized creatures cluster around the vents, feeding on microbes or on each other. Despite the extreme environment, high pressure, darkness, and sudden changes in temperature, these organisms flourish. Warmth becomes sustenance. Chemistry becomes nourishment. Sleep reminder here. Picture the deep ocean floor, quiet and dark, with a gentle plume rising like steam from a hidden spring. There is nothing you need to hold onto. Just let the image settle softly in your mind. The water emerging from vents can reach temperatures high enough to melt lead at the surface, yet it does not boil in the deep sea due to pressure. When it mixes with surrounding seawater, rapid cooling occurs. Minerals dissolved in the hot fluid precipitate, creating clouds that resemble smoke drifting upward. The chemical gradients around these vents are steep. Just a short distance away, the ocean returns to near freezing temperatures. Organisms living here must tolerate dramatic contrasts. Their proteins and cellular structures are adapted to function under pressure and heat that would challenge most surface life. Hydrothermal vent systems also play a role in the global ocean. As seawater circulates through the crust, it exchanges elements with the rock. Some minerals are removed from the water, others are added. This process influences the chemical balance of the oceans over long periods. The formation of new crust at mid-ocean ridges is continuous. As magma rises and cools, it pushes older crust away from the ridge. The hydrothermal circulation associated with this process helps regulate the temperature of newly formed rock. In this way, heat from Earth's interior gradually disperses into the ocean. Some scientists suggest that life on Earth may have originated in environments similar to hydrothermal vents. The combination of chemical energy, mineral surfaces, and temperature gradients provides conditions that could support the formation of complex organic molecules. While many details remain under study, the idea reflects the deep connection between geology and biology. You might find it calming to know that even in the absence of sunlight, life finds pathways. Energy flows not only from the sun, but also from the planet's interior. Warmth rising from magma supports ecosystems hidden beneath kilometers of water. These vent communities are often isolated from one another, separated by vast stretches of deep ocean. Species evolve uniquely in different vent fields, shaped by local chemistry and conditions. Exploration of these sites continues to reveal new organisms and unexpected adaptations. As vents eventually cool or become inactive, their ecosystems fade. But elsewhere along the ridge, new vents open. The pattern repeats quietly, heat rising, water circulating, life gathering. The deep ocean reminds you that much of Earth's activity unfolds unseen. Beneath calm waves, magma forms crust and warms water. Minerals crystallize. Bacteria convert chemistry into energy. Life persists in silence. In the next chapter, we will turn our attention to how cooling lava and solidifying rock record magnetic fields and ancient shifts in the planet's history, preserving memory within stone itself. When lava cools, it does more than harden into rock. It quietly remembers. Within its dark surface and crystalline interior, it holds traces of the world as it was in the moment of its cooling. The Earth writes slowly in stone, and each flow of lava becomes a page in a record that stretches back across deep time. As molten rock begins to lose heat, minerals crystallize in patterns shaped by temperature and chemistry. Tiny crystals form and grow, interlocking like pieces of a puzzle. Their size depends on how quickly the lava cools. Rapid cooling near the surface creates fine-grained rock, while slower cooling underground allows larger crystals to develop. These textures tell you something about the environment in which the rock solidified. Within many volcanic rocks are minerals rich in iron. As the lava cools past a certain temperature, these minerals align with Earth's magnetic field. At that moment, their internal magnetic domains settle into position, pointing toward the magnetic north of that time. Once the rock fully solidifies, this alignment becomes locked in place. The rock carries a tiny compass frozen within it. Over geological history, Earth's magnetic field has shifted and even reversed. North has become south and then returned again, though these reversals unfold gradually over thousands of years. When scientists study sequences of volcanic rock, they can detect these magnetic orientations. By comparing patterns across different regions, they reconstruct a timeline of magnetic changes preserved in basalt layers. Sleep reminder here. Imagine a quiet flow of lava cooling under a vast sky. There is nothing you need to calculate. Just picture iron crystals settling gently into alignment, holding a memory of invisible forces. The magnetic record in oceanic crust has been especially revealing. As new crust forms along mid-ocean ridges, more it captures the direction of the magnetic field at that time. As the seafloor spreads and moves away from the ridge, newer layers form beside older ones. The result is a symmetrical pattern of magnetic stripes on either side of the ridge, alternating between normal and reversed polarity. These patterns provided key evidence for the theory of plate tectonics. Volcanic rocks also preserve information about Earth's past climates. Certain minerals form only under specific temperature and pressure conditions. By studying the composition and arrangement of crystals, scientists infer details about the environment in which the magma formed and cooled. Even tiny bubbles trapped within solidified lava can contain ancient gases, offering clues about atmospheric composition at the time of eruption. When lava flows over landscapes, it may trap fragments of surrounding rock within it. These inclusions become preserved in the solidified flow, providing samples of deeper crust or mantle material. In this way, volcanic rocks act as messengers, carrying pieces of Earth's interior to the surface. Radiometric dating techniques allow scientists to determine the age of volcanic rocks by measuring the decay of radioactive elements within minerals. As certain isotopes break down at known rates, they provide a clock embedded in stone. By analyzing these isotopes, researchers estimate when a particular flow cooled. The rock becomes both archive and calendar. Over time, layers of volcanic rock accumulate, each representing a separate event. In some regions, stacks of basalt rise hundreds of meters thick, formed by repeated eruptions over millions of years. Between flows, the soils may have developed briefly, only to be buried by the next surge of lava. These interlayered soils and rocks preserve a rhythm of eruption and rest. Erosion gradually exposes these layers, allowing geologists to read them like chapters in a book. Cliffs reveal cross-sections of ancient flows, each with distinct textures and compositions. By studying these exposures, scientists reconstruct patterns of volcanic activity and tectonic movement across vast timescales. Volcanic ash layers found far from their source also serve as chronological markers. Because large eruptions can distribute ash widely, the same thin layer may appear in sediments across different regions. Identifying and dating these layers helps synchronize geological records from distant places. Even the orientation of volcanic dikes and sills within the crust reveals past stress directions. As magma intrudes along fractures, it follows pathways shaped by tectonic forces. Once solidified, these intrusions record the orientation of those forces at the time of emplacement. You may find it calming to realize that the ground beneath you hold such quiet memory. Every rock has a history, not in words, but in minerals and magnetism. The Earth does not forget easily. It writes its story slowly, allowing future generations to read it with patience. As you rest with this image, picture a vast library of stone stretching beneath continents and oceans. Each volume is heavy and silent, yet filled with information about shifting poles, drifting plates, and cooling magma chambers. In the next chapter, we will return to the present moment and consider the long calm of resting mountains, where volcanoes spend most of their lives in stillness beneath open skies. Most volcanoes, most of the time, are quiet. If you stand before one beneath a clear evening sky, you may see nothing more than a dark silhouette rising gently against fading light. Snow may rest along its summit. Forests may cover its lower slopes. Streams may wind down its flanks, reflecting the stars. It is difficult to imagine that this peaceful mountain was once a place of flowing fire. Yet the calm you see is not unusual. It is the dominant state. A volcano becomes dormant when it has not erupted for a long period, but still retains the potential to awaken. The magma beneath may cool and crystallize partially, forming a dense, semi-solid mass. Heat remains, but it moves slowly now, circulating quietly through deep chambers. There are no visible plumes, no trembling ground, only subtle geothermal warmth in some places where hot springs or faint steam remind you of what lies below. Time stretches widely across such landscapes. Decades pass, centuries unfold. Generations grow up knowing the mountain only as a steady presence. Soil deepens along its slopes. Roots anchor firmly. Wildlife finds shelter in craters once shaped by eruption. What was once molten becomes meadow, forest, and stone. You may notice how stillness feels different when you understand what rests beneath it. The mountain is not inactive in an absolute sense. Internal heat continues its slow journey outward. Minerals adjust at microscopic levels. Tectonic plates shift far below, though their motion is too gradual to see. Even in apparent rest, the planet remains alive. Over thousands of years, erosion reshapes dormant volcanoes. Wind and rain carve channels through hardened lava. Frost widens cracks. Glaciers may grind against slopes during colder climatic periods, smoothing and sculpting the terrain. The sharp edges of past eruptions soften into rounded contours. In some cases, a volcano thought dormant may stir again after a long quiet. Magma may rise slowly, bringing renewed heat to shallow depths. Small earthquakes may signal movement, yet such awakenings are rare compared to the long spans of rest. For every eruption that captures attention, there are countless years of silence. Sleep reminder here. Let your body feel as steady as a mountain under snow. There is nothing you need to anticipate. Just breathe in gently and exhale slowly, unlike heat dissipating into cool night air. Dormant volcanoes often become places of beauty and reflection. Lakes fill ancient craters, their waters calm and clear. Trails wind along ridges formed by old lava flows. People gather not in fear, but in appreciation of the view from the summit. The memory of fire becomes part of the landscape's depth rather than its present expression. Geological records show that volcanic cycles can span hundreds of thousands of years. A system may remain active for a time, then quiet for long intervals, then reawaken under the right conditions. These cycles are influenced by mantle heat, tectonic stress, and the gradual replenishment of magma chambers. Yet, from your perspective, lying here at rest, these cycles unfold at a pace beyond urgency. Even after complete extinction, when a volcano will never erupt again because its heat source has dissipated, its form remains etched into the land. Ancient volcanic cores stand as eroded hills. Basalt plateaus stretch across continents, remnants of long-cooled flows. The fire has gone, but the structure endures. You might find comfort in this pattern. Intense moments are brief. The long calm surrounds them on either side. Power is not constant eruption. More often, it is quiet endurance. Mountains rise, glow, cool, and then rest for ages beneath open skies. Above a dormant volcano at night, stars scatter across the darkness. The same gravitational forces that shape planets and moons hold this mountain in place. Beneath the crust, warmth remains, but it does not rush. It waits, circulating slowly, part of Earth's steady balance. As you reflect on all you have explored, magma chambers deep below, lava rivers cooling into stone, ash drifting through quiet skies, islands rising from oceans, life returning to blackened slopes, distant worlds shaped by hidden fire, you come back to this still mountain. It stands not as a symbol of destruction, but as a reminder of patience. The Earth is not in a hurry. Its processes unfold over spans that allow renewal and rest to follow heat and change. Dormant volcanoes teach you that stillness is not emptiness. It is simply a different phase in a longer rhythm. And now, as this journey gently comes to a close, notice how wide and still the world feels. So many mountains standing quietly beneath the sky, their warmth hidden deep below. You don't need to remember every flow of lava or every drifting ash cloud. They have already done their quiet work. If you enjoy these slow explorations, you can support the channel in any small way that feels natural, so others can find this calm too. But right now, there is nothing to decide and nowhere to go. Let your thoughts soften, your muscles relax, and the night carry you onward, one peaceful breath at a time.